Is the second half of factors affecting enzyme catalyzed reactions. This is 1B. In this one, again, we'll be here describing how, in this case, temperature and pH are going to affect initial rate of the reaction. Pardon me. And then down here explaining B, why initial rates of the reaction are lower outside of the optimal temperature range and the pH range. So coming back up here to 2C just a second, we'll be discussing here this optimal range concept. In the previous screencast, we discussed that Vmax sort of concept and this concept of saturation. So that's in the previous one. So today, or for this one, we'll be looking at those items right there. So again, just from previous screencasts, again, enzyme active site specific conformation. The word I keep saying, by the way, is conformation. Somebody asked me about that. Like, what are you saying there? Conformation. Form, right, meaning structure. Okay? So the structure, the shape, the form of this active site is important because the substrate, of course, is going to fit into this active site when the enzyme and the substrate collide with one another, and then you're going to yield the products down over there. So here we go. Enzymes. Most enzymes are protein-based, and from earlier we were discussing really that proteins become functional at this tertiary level of structure, and here we see this ribbon model of that. And we had discussed earlier that the tertiary structure, of course, is maintained by interactions between R groups here. So hydrogen bonding between R groups, ionic bonding between those R groups, disulfide bridges between those R groups, and then this van der Waals interactions, weak interactions between nonpolar side chains. So these interactions, these four classes of bonds between the R groups maintain that conformation of the enzyme. This is going to be important as we see here in just a little bit. So the maximal rate of initial rate of catalyzed reactions is a function of the temperature or the pH. So again, this is from a previous screencast, but let's just assume that we have a solution here where we have enzymes and we have substrates, and some assumptions here that we're going to make when doing these temperature and pH experiments or scenarios is that the substrate is overloaded. So we're not going to run out of substrate. Substrate's overloaded. Therefore, we can almost guarantee Vmax is going to be reached, and you're not going to run out of substrate. You're going to have this reaction happening maximally, and you're going to get lots of collisions between enzymes and substrates here, so that you can then measure the rates of the reaction. So the question is, all right, what's going to happen if we increase or change rather, just temperature change or the pH change of this environment, environment around the enzyme. So based on your readings, you should be able to predict what's going to happen. So here we're getting, again, rates of the reaction that we're monitoring over the different temperatures, right? And we're going to talk about this concept of optimal temperature here. Right, now this is two different enzymes in this scenario right here. So we have scenario one, here's the optimal temperature for a typical human enzyme. Right? And so let's talk about this optimal, it's really an optimal range, right, that exists. This is not just one specific temperature, but a window of range here. So what we're saying is that for this human enzyme, if you look, this is where it's working maximally. This is the maximum rate there, and this somewhere in this temperature range right here, and you drop this down, and lo and behold, where is that? That's around 37 degrees C, which is body temperature, 98.6 degrees Fahrenheit. So you see that with then another enzyme over here, enzyme 2, another scenario, another situation. Optimal temperature for an enzyme of a thermophilic, heat-loving, heat-tolerant bacterium. So over here, this enzyme is a different enzyme, and it has a different optimal temperature range, right, somewhere in the neighborhood of 75, right, degrees C. Right? So two different enzymes, two different organisms, evolving in different environmental conditions to have enzymes that are working maximally at this optimal, again, not just one specific thing, but an optimal range. So the question is, once you go beyond the optimal range, so beyond either this way or beyond either this way, right? So if you go lower than the optimal range or above the optimal range, what happens? Well, obviously what's happening when I go below there, what's happening is the rate of the reaction is dropping off, right? The rate of the reaction right over here at a lower temperature, right, is lower. Right? But when you go beyond, above the optimal temperature range over here, that rate is also lower when you get up here in the 40s, maybe closer to 50. Right? So describing the curve is that, as the way that you describe this, let me say either one of two different ways. You could say as the temperature increases, the temp increases, rate increases to a max, right, then decreases. Right? You could change this a little bit more, and you say as the temp varies outside of an optimum or optimal range, right, rates go down. Right? Another way of describing that, rate is maximum within an optimum temperature range. Right? This first one is probably the most descriptive of actually what the curve is doing. Right? The second one as well. Right? Different enzymes have different optimal temperature ranges depending on where they are coming from. So this is just describing the curve. This is just describing, but then the question is, all right, explaining biologically what's going on here. Why? Why does the rate of the reaction vary or decrease once you leave that optimal temperature range? Right? Well, for this, the explanation, and I'll use this curve to the right over here of the thermophilic bacterium, but the concept is going to be just the same. So you want to divide this into, at a minimum, two different sections, right? So I would say, right, why is it increasing, and then why is the rate decreasing as I increase the temperature, right? Or why outside the temperature, the optimal temperature range? So the explanation for what's going on over this part of the graph is different than the explanation for what's going on over on this part of the graph. So I'm going to have two different explanations. So explanation A for this part of the curve and explanation B for this part of the curve. Explanation for part A of the curve goes something like, or it has something to do with, the kinetic energy of the system. And so what's happening is that as you heat the system, the molecules, right, in that system, let me just go back a second. Right? Visually, I'm picturing this in my mind's eye so that these enzymes and substrates are moving randomly in this solution. And as you increase the temperature, the movement of these enzymes and substrates is going to increase. The kinetic energy increases. These things are moving more quickly, more rapidly, so that increases the likelihood of collisions. Right? So by increasing the kinetic energy of the system, right, you increase the likelihood of collisions between enzyme and substrate. Well, if you increase the likelihood of collisions between enzymes and substrate, then you're going to get more, right, induced fit between enzymes and substrates, and you're going to get more product made, right, per unit time. So all of this is per unit time. This is why the rate is increasing, right, as you increase the temperature. You could also explain it the other way. As you decrease the temperature from the optimal range, the kinetic energy of the system is lowering, so you have fewer collisions between enzymes and substrates, therefore fewer induced fits, and therefore fewer products made. Again, per unit time is the thing that kids often leave off there and are missing. So that's explanation for part A. For part B of the curve, right, why? What's going on up here? The explanation is, well, there's so much kinetic energy, right? So there's too much kinetic energy. The enzymes, right, moving so rapidly, right, that there are shear the shear forces, right, break BRK are going to break bonds of the tertiary structure of the protein. Therefore, if you change the tertiary structure of the protein, you change the active site conformation. Therefore, you don't get any induced fit. Therefore, there aren't very many products made per unit time, and by definition, then your rate is going to drop down. Right? Your rate's going to go down. So what's happening here, long and short of this, is that the enzyme denatures. We say that above the optimal range, the enzyme is going to denature, right? And the active site conformation will not then fit the substrate, etc. So that's a lot to take in. You can pause if you need to, but I'm going to move on to pH. So these curves for pH look very similar to the curves for temperature, right? Where again, there's going to be an optimal pH range for these things, for these enzymes, and we're looking at two enzymes here, right? So enzyme 1 for pepsin. This pepsin is an enzyme that's found in the stomach and begins to break down proteins in the stomach. This enzyme trypsin over here is an enzyme that's found in the small intestine. They have two different pH optimal ranges, right? The pH range for the stomach, as many of you know, is the stomach is an acidic environment. And so the pepsin here has this pH range of around 2, right? Plus or minus a little bit. Well, in the small intestine, the pH range is around 8. Well, lo and behold, where trypsin is most active is in the small intestine, and this range is around 8. This is not a coincidence. So, explaining, so again, well, first of all, describing the curve here, right? Describing the curve, I'll let you give that a shot, right? So based on what we described before, how would you write this description of the pH curve and then the explanation of the pH curves? I will tell you that this pH is going to be affecting changes in pH, which pH, if you don't know, is a function of the hydrogen ion concentration. So if I'm dealing with hydrogen ion concentrations, right, I'm going to be changing that in the environment of the system. And so if I'm doing this, I'm playing with this, this is going to be affecting hydrogen bonds. It's also going to be affecting ionic bonds, right, between R groups. Right? So the explanation here sounds a lot like the explanation from what? You finish it. Look at that. Go back and think about what you would write there. Okay? So how would you describe these curves, and then what's the explanation for why they look the way that they do? So this will animate itself here. I don't know how I got this to work, but I somehow did. I think I just copied it in there. But again, this is your whole like denaturing visual here at the bottom. Yay. I don't think it's going to repeat, but I'll do if I just click back and go here. So again, with an optimal pH, here's your enzyme. Here are hydrogen ions changing. Look, that's changing the shape of the active site. And will that substrate, oh, so sad, no reaction, okay? So again, this denaturing, renaturing concept there. You saw this in a previous screencast, so here's an opportunity for you to practice. All right, how would you label this axis? How would you label this axis? What are these lines, right? What are you going to do with that information? There's another blank set of axes. What would go here? What would go here? What curve would you put on there? And then we looked at this beforehand. Now you're maybe ready to do this for an increased temp, decreased temp, increased pH, lower pH beyond what you have here, right? And then place for you to explain that. Okay. Hope that was helpful. If not, ask questions. How do I stop?